Hello everyone. Hey Physics 103. What we're just going to talk about after having our first week, I'm just going to give a little audio tutorial going through the worksheet assignment, the extra credit one. For the first worksheet, first of four, the above plot, it's a way of representing how someone's position, some object's position changes with time, and how we interpret it is in the first second, some object was at some 4 position and it moved backwards until it reached the -8th position. And then in the very next second, it moved forward to the -2nd position, stayed still for a second, kept moving forward until it was at the 8-meter mark, stayed still, and then kept moving backwards until it was at the -4-meter mark. In order to calculate total distance, this is where we're going to be summing up all the jumps, whether downward jumps to the next point or upward jumps to the next point. And if it ever is negative, we'll take the absolute value. So for the first line segment, we are ending at the -8th mark, and we are going to subtract that by the 4 mark. Then for the next part, we go from -8 to -2. So that's why it's -2 minus -8, absolute value signs, plus. And then this line is just going to equal 0, but the second point is -2. The first point is at -2, so that's going to be 0 for there. Adding the next line segment, this is going to be from +8 minus -2. So +8 minus -2, and then plus the last two. Well, these 2 points, this line segment, it ends at 8. It also starts at 8. So 8 minus 8, and then this line segment, it ends at -4, which is why I have -4 here, minus 8, because this line segment started at 8. Now, as we figure all this out, we're going to get 12 plus 6 plus 0 plus 10 plus 0 plus 12, so your answer should end up being 40 meters. Displacement is pretty straightforward. All we need is the final vertical position and the initial. Well, at the end of our measurement, we are at the -4 mark. And at the start, we are at the +4 mark. So -4 minus 4, that comes out to -8 meters. So in the grand scheme of things, despite this object moving backwards and forwards and backwards, overall it displaced backwards by 8 meters. Average speed is going to be pretty easy once we have our total distance of 40 meters. The entire run that this was measured was 6 seconds, so 40 meters divided by 6 seconds gets us to 6.66 repeats meters per second. And for average velocity, well, that's going to be our displacement, -8 meters, divided by 6 seconds is how we got -1.33 repeats meters per second. As far as all of these different values for instantaneous velocity, well, these are just going to be the slopes. For our first line segment, how we got -8, 4, 1, and 0. Well, at time t equals 0.5, that's somewhere in this region, so it's somewhere along this line segment. It ends at -4. It starts at +4, so 8 minus 4 for the numerator. And then as far as the time axis, it ends at 1 second. It starts at 0 seconds, so 1 minus 0. And that's how we get 8 minus 4 is -12. 1 minus 0 is 1. -12 divided by 1 is 12. For time t equals 1.5, 1.5, it could have been 1.3 or 1.9. Any point in time where our plot is along this line. Well, start with the second point. Its height is at -2, and the first point, its height is at -8. So negative 2 minus 8. As far as the time axis, this ends at 2, it started at 1. So that's why we have negative 2 plus 8. So negative 2 minus a negative 8 just becomes negative 2 plus 8. And then 2 minus 1, that's how we eventually get 6. And then the remainder, pretty straightforward, similar process. To get the instantaneous speed, well, it's just taking the absolute value of all of our instantaneous velocities at those points in time. And well, absolute value of negative 12 is just 12. Absolute value of positive 6 is just 6. Absolute value of 0 meters per second is 0 meters per second, and so on and so forth. For the part about constructing a velocity versus time plot, well, alright, what we need is our instantaneous velocity values. What we see from 1 to 0, as far as time, our value is negative 12. So, negative 12 for the entire 0 to 1 second. From 1 to 2 seconds, we calculated our instantaneous velocity as positive 6. And then between 2 and 3 seconds, we got 0. And then between 3 and 4 seconds, we got positive 10. Between 4 and 5 seconds, it was at 0. And between 5 and 6 seconds, it was again at negative 12. And then just labeling our graph v of t in meters per second and time t in units of seconds. For the next worksheet, that's the vector addition one, we have two vectors. We have one, the vector A, and then vector B. Vector A has a magnitude of 8 meters per second and a direction of 60 degrees above the x-axis, positive x-axis. Vector B has a magnitude of 3 square root of 2 meters per second and is 45 degrees below the x-axis, positive x-axis. And this is what we're supposed to get in the end. As a guide, that's what this page is for, to slowly build up the answer. So, for the y component vector, for VA and VB, let's look at this. For VA, we have an arrow that's pointed up. So that's going to be a positive y component. Whereas for VB, we have an arrow that's pointed in the downward direction. So that's going to be a negative y component. Now, in order to get the y component, we're going to take, for VA, VAY will be 8 meters times sine of 60 degrees, and because it's pointed up, times positive 1. For VB, the y component will be 3 square root of 2 times sine of 45 degrees, and then times negative 1 because it's pointed down. And if we do that, we roughly get positive 6.928 meters per second for VAY and negative 3 meters per second for VB. Essentially, the negative here, I didn't initially have it in the calculation, but I just added the negative sign afterwards just to keep the direction. If you just solve like this without adding that plus 1 or minus 1 at the end, that just gives you the magnitude. So just remember to include the sign of the direction in your final answer though. For the component vectors of VAX and VBX, well, taking the initial value of VA, that's 8, times its angle, cosine of 60, gets us 4. And then for VBX, that would be 3 square root of 2 times cosine of 45 degrees, which gets us 3. The reason why both of these are positive is because for both vectors, they're both pointed toward the right. The right would be the positive x-axis direction. Now at this point, we can just keep going. Our y, the sum of the y component vectors, we only had two vectors, VA and VB, so we just need to add VAY plus VBY, which gets about positive 3.928 meters per second. For Rx, the sum of the component vectors in the x direction, VAX plus VBX, is positive 4 plus 3, or positive 7 meters per second. The resultant vector is just going to be the x component squared plus the y component squared. So 7 squared plus 3.928 squared. Adding those two together and then square rooting all of that, you should get 8.03 roughly meters per second. And then the angle, theta is going to equal arctan, or it may be written on your calculator tan inverse, like as shown here. In either case, that function of the y component divided by the x component. So arctan of 3.928 divided by 7. And then your answer should come out to 29.3 degrees. Again, as mentioned during lecture, for this type of trig, whenever you're using trig functions, just remember to have your calculator set to degrees and not radians. If you're getting different answers than what I have, that might be what the issue is. And now, lastly, it's just drawing the resultant vector, which, here's how I basically did it. I looked at Rx and Ry. Rx came out to positive 7, so I'm going to draw an arrow to the right. And then Ry came out to positive, almost positive 4, positive, so I'm going to go up. So, an arrow that's arbitrarily some length, so I'm going to pretend that that's 7. Therefore, the arrow that's about 4, that should be a little bit smaller. Rx was positive, so to the right. Ry is positive, so up. Connecting from the tail of the first component vector to the arrowhead of the second component vector. That's how we draw our resultants. And then I just labeled its value, and I labeled the theta r, the angle for this guy, 29.3 degrees. And then that would be that worksheet. Next one, now we're getting into the single-sided worksheets. Well, similar to the first part, where it was from position getting velocity, well, let's say we already start with velocity. Velocity versus time. We have some object that its velocity is about -3, and it's increasing until it's at positive 7, and that went from 0 to 2 seconds. Then from 2 to 4 seconds, it stays at positive 7 meters per second for the velocity. Then over the next second, the velocity decreases until it reaches 0. And then between 5 and 6 seconds, it stays at 0. And then between 6 to 8 seconds, it goes from 0 meters per second to -12 meters per second. And then it stays there between seconds 8 through 10. What I have drawn here is basically the slopes, because that's going to give us our acceleration value. In order to answer the question, create an acceleration versus time graph using the above velocity data. Well, calculating the slopes, this line segment, the top height is 7 minus the bottom height, -3, and then the time length, 2 minus 0. That came out to a slope of positive 5 meters per second squared. This horizontal line, well, we already know that that's just going to be 0, and that's spanned from 2 to 4 seconds. From 4 to 5, the height dips from 0 meters per second minus 7 meters per second. And then 5 minus 4 for seconds gets us -7 meters per second. Between 5 and 6 seconds, it's again horizontal, so a slope of 0 meters per second squared. And then between 6 to 8 seconds, we go from 0 to -12 meters per second for the height, so -12 minus 0 in the numerator. And then the time went from 6 to 8 seconds, so 8 minus 6. And then solving this, you should get -6 meters per second. Don't forget to have the top in parentheses and the bottom in parentheses if you're doing this on your calculator, just to maintain order of operations. And then between 8 and 10 seconds, the velocity doesn't change, So that will be 0 meters per second squared for the acceleration. Bringing those slope values, here's how I drew the acceleration plot. I have a of t for the y-axis in meters per second squared, and for the x-axis, time in seconds. Well, from 0 to 2 seconds, we were at positive 5 meters per second squared. Then between 2 to 4 seconds, acceleration should be set equal to 0. Then between 3 and 5 seconds, acceleration is going to be negative 8 between those points in time. Between 5 and 6, the acceleration or the slope on the velocity versus time graph was 0. Between 6 to 8 seconds, the value was at negative 6. And between 8 to 10 seconds, we calculated it as 0 meters per second squared. So, part B, assuming the mass of the graphed object was 85 kilograms, what force did the object experience? All right, well, the force, we're going to calculate it at these different points in time. Time equals 1 second, 3, 4.5, 5.5, 7, and 9 seconds. So force at 1 second. At 1 second, we see that our acceleration is positive 5. So 85 kilograms times positive 5 meters per second squared gets us a force value of positive 425 newtons. At 3 seconds, our acceleration is 0. So 85 times 0 is 0 newtons. At 4.5 seconds, we are at this point. So acceleration equaled negative 7. 85 times negative 7 meters per second squared gets us to negative 595 newtons. At 5.5 seconds, well, our acceleration is 0. Therefore, our force has to equal 0. At 7 seconds, it could have been 6.9, it could have been 7.3, but what matters is at time equals 7 seconds, our acceleration is negative 6. So 85 times negative 6 gets us negative 510 newtons. And lastly, at 9 seconds, well, the acceleration is again 0. The acceleration is again 0, so the force is going to equal 0 newtons. And our last worksheet, just to get into free body diagrams and a little bit of friction. In each situation of a sliding block or rolling wheel, calculate 1, the force of static friction, and if the object will move, then 2, the linear acceleration once the object is in motion. 3, also draw in the relevant forces acting upon the object in motion, like force of gravity, or the y component and x component for sloped, as well as the normal force and the force of friction, being sure to clarify if it's friction, static friction, or friction in motion, or kinetic friction. Let's look at our first sample. We have a block that's on a horizontal surface. We're assuming that the acceleration of gravity is 10 meters per second squared, just to round it. So a 50 kilogram block times 10 meters per second squared, force of gravity is 500 newtons. Now, because our object is not changing height along the y-axis, and we don't have any additional forces in that axis, then this force of gravity has to be canceled out by our normal force of 500 newtons. We also have an applied force of 475 newtons pulling to the right, which means that we are going to have some friction force pulling to left. To actually determine that, we have our force of friction, FF, our force of static friction, F sub Fs. Calculating that, it's our coefficient of static friction, μs, multiplied by the normal force. So 0.5 times 500 newtons. Static friction is 250 newtons. 250 newtons is not enough to cancel out the applied force of 475 newtons, so the object will move. Therefore, we should calculate our force of kinetic friction, or in this case, because it's mu sub m, then force of friction in motion. That's just coefficient of friction in motion, 0.15 times the normal force, 500 newtons, and that gets us to 75 newtons. Rearranging our force equals mass times acceleration equation, acceleration in the x-axis is the net force in the x-axis divided by mass. The only x forces we have is our applied force pointed to the right, so we're going to make that positive, and our force of friction in motion pointed to the left, opposing motion, so we're going to make that negative because it's pointed to the left. 475 minus 75 is 400, divided by the mass, 50 kilograms, gets us positive 8 meters per second squared. And then just write your answer up in this top corner here where AX is present. And then lastly, let's have a sloped problem. We have a slope with a gradient of 40 degrees. We have no applied force, so this object is just experiencing gravity. Well, first things first, gravity. We have a 50 kilogram block. Gravity is a force that goes straight down, and timesing that by acceleration due to gravity, which we're rounding to 10 meters per second squared, that comes out to 500 newtons. Now, for these sloped problems, unlike when we were on horizontal surfaces and the force of gravity was perfectly balancing the normal force, that's not the case. In this case, we have our modified y component of gravity that is actually pushing into the surface. To calculate that, we take our force of gravity, 500 newtons, and because we're not using a angle touching our vector, but we're using our angle gradient, we should not use sine for y in this case, unlike every other situation. For this specific situation, we'll use cosine. So 500 cosine of 40 degrees, that comes out to roughly 383 newtons. So I see a little typo with the answer key right there. I wrote 321. I better correct that. Okay, made that slight change. The y component of gravity should come out to 383 newtons. And because this is the y component that's going into our slope, that is what normal force is being matched by. So normal force equaling the y component of gravity equaling 383 newtons. Now, force of gravity in the x direction, we're going to need that eventually. So while usually for x components we use cosine, for this specific scenario and only for the gravity vector, use sine. So 500 sine of 40 degrees, that gets us to roughly 321.4 newtons. For force of static friction, if we use our coefficient of static friction, 0.5, times the normal force, 383 newtons, that comes to 191.5 newtons. Well, there's 321 newtons of force pulling the object down the slope. Friction can only keep something still if it's only up to 191.5 newtons. 321 is greater, so the object will start sliding, which means our actual force of friction will be kinetic friction or friction in motion. Therefore, we are going to calculate using the coefficient of friction in motion, 0.15, times our normal force, 383 newtons, and that gets us an answer of 57.45 newtons for friction, the direction being up our slope. Therefore, acceleration in the x direction being the net force divided by the mass, the net force in the x direction, we're going to assume any force that pulls down the slope is positive, so we have gx, and then any slope pulling up the slope would be negative, so minus force of friction in motion, FFM. That becomes 321.4 minus 57.47 newtons. Have that both in parentheses, and then you can hit divide by 50 kilograms in the calculator. And this is going to get us positive 5.28 meters per seconds squared. And therefore, in our answer, positive 5.28 meters per seconds squared. In any case, hope that all helps you out for understanding the answer key. Glad to have you all in class, and wish you another good week. Peace.